Hello, everybody, and welcome to the 48th episode of the Hyperthesis podcast. I'm Liam.
I'm Feely.
And I'm Patrick.
So today we're going to be talking about the kind of science behind photos and photography. But before we get into that, we have our intro topic, which someone has prepared that isn't me.
Well, Liam, you have some corrections for last episode, right?
Oh, right. Thank you. All right. So last episode, I don't even remember what we talked about, but I said something about how, in general relativity, when you study the theory of inflation slash the beginning of the universe, you can have this absolute slash preferred frame of reference. But that is definitely not correct. So I was talking. I think I was saying the words absolute or preferred, but I was thinking co-moving. So I made a mistake saying that. I meant to say there's a co-moving frame of the universe, which is something I'll admit I don't fully understand. But essentially, you can identify a frame of reference of the universe during inflation, where an observer sees the cosmic microwave background to be isotropic everywhere, so the same in every direction. And the only reason why things move away from each other in this frame is due to the expansion of the universe. Or in other words, this co-moving frame kind of factors away the expansion of the universe, giving a distance that doesn't change in time due to the expansion of space, so that everything looks the same from your point of view, or isotropic. So structures might change due to other kind of local factors, such as like galaxy motion and other things like that. But as far as the expansion of space is concerned, everything looks the same. So it's this isotropic frame that co-moves. You can think of it like fluid mechanics. There's a frame of reference in fluid mechanics that you can move to that is called the fluid frame, where you kind of move along with the fluid. So if you took a little box, it's as if nothing's changing. There's nothing going in and nothing coming out. It's not moving. Whereas if you're in the lab frame on the side of a river, if you put a little box, imagine you like drew a little box in the river, there'd be stuff going in one side and coming out the other.
So which frame are we basing on? Which frame are we basing the age of the universe on?
Oh, so this co-moving frame, it's kind of nice because it's this kind of universal frame. So regardless of where you are in the universe or in space-time, aside from maybe inside of a black hole, I guess, because if you're inside one of those, things get weird. But aside from that, no matter where you are, everyone can kind of agree on this co-moving frame, and do the math that gets you to it. So this is the exact frame that when we say the universe is about 14 billion years old, it's from this co-moving frame's point of view. It's kind of this like nicer frame to talk about. I'm not sure about. I haven't done the calculations for this. This is just what I read online. But it's probably roughly the same from the Earth's point of view, although I'm not sure.
I have no idea.
It's like 13 point something billion years, and from our frame of reference, it might be an extra like 0.1 billion years or something, but it doesn't make a huge difference. I don't know. That's my guess. Maybe that's something I'll look into.
All right.
But yeah, so that was my correction. And now, who has an intro topic?
Yeah, so the intro topic today is I found it a few days ago. It was on the photonic ships. And for those who wonder what they are, because I was wondering what they were, but I heard a bit about it before. I didn't really know about the application for it. So a lot of data centers and data transfer now kind of reaching some limits, right? Like people want to transfer more data and people want to transfer things faster. And one of the limitations that people run into is called bandwidth. So how much, we call this called the bandwidth bottleneck. So it limits the performance and scaling of these systems. So basically, when you want to run things that, connect systems that are far apart and you want to transfer a lot of data to it, now people have used like fiber optics, for example, to transfer those stuff. But fiber optics use light, and you can have many frequencies of light, and you can manipulate them to transfer your data. So, but these nodes can be separated, like nodes between system can be separated more than like 1 kilometers, right? Like, and each metal wire is not perfect, so it's going to dissipate electric signal as heat. So when you try to transfer data at high speed, so even you use fiber optic cables, a lot of energy is wasted in the process of converting this like electrical data into optical and vice versa. So so people have to come up with the energy efficient method for transferring these type of data over fiber optics cable. So normally, the one that we use so far, we basically transmit signals over multiple wavelengths of light. So normally we use like different laser to try to generate each wavelength of light, which makes sense. But with the new technique of photonic chips, we actually can use one single laser to generate hundreds of distinct wavelengths of light. Sounds kind of strange, isn't it? But it happened. So basically, you can put like one light, one wavelength, like one laser light in to do these photonic chips that have like certain optical arrangement and such, and it would split out many wavelengths. At least that's in my understanding. So they managed to transmit 16 gigabytes per second per wavelength for 32 distinct wavelengths. So it's like 512 gigabits, not gigabytes, yeah, gigabits per second, with less than 1 bit error out of 1 trillion transmit bits. So that's pretty good. And I think the normal bandwidth we have for one web, for like a single fiber is around 100 gigabits. So this is like a 5 time improvement in one single fiber. And the chip that's being used is like it's just a small chip measuring like 4 millimeters by 1 millimeter. So yeah, so it's gonna be a quite improvement if it can be scaled.
That's kind of wild to think about, given that, like, for example, living in a city right now, we get gigabit internet over fiber optic, and that's 1 gigabyte or 1 gigabit per second. And here they're doing 512 gigabits per second. That's just an insane amount of data to think about.
Well, also that's for one wire, right? Like normally fiber optics have many entwined together, right? So that, yeah.
This is a little unrelated. Well, it's related, but kind of off topic. There's that big cable. There's a big cable that I always hear about this, and I've never actually looked into it. The one that's at the bottom of the ocean, right?
There are
That
many of
goes.
them, yes.
Yeah, well, I was about to say, surely there's not just one, because something goes wrong with it. You now have it. Where does it go from again?
I mean, there's entire maps of it, but I mean, they go across the Pacific, they go across the Atlantic. I believe there's some in the Indian Ocean as well. But essentially,
But
they connect all the continents in different ways. So, for
yeah, so they
example, if one were to go down in the Atlantic Ocean, then you can still get internet, but it has to kind of go all the way around the world.
but like this cable, it connects like basically Europe to like North America, right? That's a massive cable, and they're fiber optical cables. Um, and there's probably a few of them, right? Because if something goes wrong, you always have more. But I wonder how much information those process, and how do they upgrade them when you get kind of things like this? When you get more technologies where you can transfer more information faster, surely they don't pull the whole thing up and like replace it all at once. They do little bits at a time or something. I don't know.
You don't need to. I mean, the wire, they don't change. What changed your centers, right? The way you transmit data.
Hmm.
Like, so the actual wire is the
Hmm.
same. Like the
Yeah,
fiber optics is just a cavity that, that does the total internal reflection. That's the same thing.
but
But
surely they need to like repair them sometimes, or like I've heard
yeah,
sharks bite those things, or like maybe not sharks, but like things at the bottom of the sea that are sensitive to electromagnetic signals. They like bite these um big cables sometimes, and the cables I think they're armored pretty well, but still, like surely you need to bring them up sometimes. And the ocean's really deep, and it's really far between here and the Europe, right? Like that's crazy to me that this technology's gotten so advanced that you can do stuff like that, let alone transfer hundreds of gigabits per second.
Just based on off of what I've heard and what I can tell, it looks like they don't really replace the cable. Like if it's a major cable, they'll try and fix it if it's feasible. But for the most part, they'll just lay a new cable if there's major upgrades. And looking at a map of the different cables, it looks like they have different capacities. So kind of on the lower end is 250 gigabytes per second and below, whereas you can get cables with more than 3,000 gigabytes per second. So
Holy
I'm
crap.
assuming that those ones are newer and therefore higher capacity. But there's definitely variable ones. But from what I understand, it's so costly to like bring that up that they would probably just put a new one in instead of trying to like make major fixes or replacements to it.
They just leave their garbage at the bottom of the ocean. Classic.
The point of photonic chips here is to actually make it energy efficient. Like I said before, transferring data, you lose a lot of energy, then that can contribute to errors, right? And especially with the rise of artificial intelligence, and you have to take a lot of data to train AIs, and so there's been large amount of data being sent all the time just to train the AI, which maybe wouldn't work. But like, so there's like the use of data transfer have been like has like exploded over the past few years.
I'd be very interesting to see with these photonic chips what the error rate is like over different distances, because that's something with our fiber optic networks that we require are repeaters, which essentially take in the signal, reamplify them. So I'd be curious with these photonic chips, like if they can, one, be more efficient, but they can also have less error for longer ranges.
I think because of you have light traveling through this medium like these fiber optical cables. I'm not an expert, but I think you're always going to need a lot of repeaters. I think the information will always get kind of messed with in some sense, especially because like you think of for the physics of fiber optics is basically you get total internal reflection, right? This light kind of bounces through a cable as it travels, but as it hits the edge of them, you get this evanescent wave that kind of comes out the other side a little bit. So you're always losing a bit of energy as it goes, and a bit of you're getting a bit of decoherence no matter what. I think even if you get these photonic chips involved, I still think that's going to happen. So I mean, maybe I'm wrong, but I think you'll always need some kind of amplification along its journey.
Oh, yeah, for sure. But if it's more efficient to create these, can we input the same amount of power but get higher intensity beams out of this that are totally internally reflecting? So that way they can go for longer while still losing that energy because of their higher intensity.
And also, like, photonic chip can process things like signal at speed of light, basically, right? Like, to me, it's even better than electrical signal. Well, the problem that you mentioned, Liam, is like, yeah, what about coherence? Because that's gonna be the problem with using lasers. If you want to code something or transmit certain signal to laser, well, how you gonna modulate your lasers, right? Like, well, over a long length or long duration, can it still be coherent? Coherent, like, one of the big property of laser. So let's see what happens in the future.
I'm just curious, from this, did they mention how varied the wavelengths are? Because it says it has distinct wavelengths, but is it like nanometers difference in terms of wavelength? They're like tens of nanometers, or just like very, very fine differences, but still distinct?
I am not sure, actually. I think you have to
Probably,
go read the paper.
I find in these laser papers, um, when they want to get really like specific wavelength, they still usually have errors of usually like tens of nanometers. Um,
It looks like 1 or 2 nanometers.
that's pretty good.
Yeah.
Yeah, so that's I think our previous guest we had Dean. One of his research topics is to get like it's to I mean I'm probably butchering this explanation, but it's basically one of the goals is you get less error on either side. You get like a more peaked wavelength instead of like the plus or 10 nanometers. You get like plus or minus 1 or 2 or something like that. So that's pretty good if they got that.
I think the limitation is like also how precise can you perform the Fourier transform, right? Like, can you pick up signal out of this like mess of the thing?
Yeah, well, I was talking to Dean about this a lot actually, and maybe the stuff he's trying to do is different. He's trying to make like probably intense laser pulses, but also keep them as narrow as possible so they're not so broad. So everything's down to like a very small frequency range. But he was saying that so when you have these Fourier transforms, basically like in quantum mechanics, you have an uncertainty principle that tells you like you have the Heisenberg's uncertainty principle. You can't know the position and momentum of a particle perfectly. If you know one really well, you don't know the other very well. So if you know the position of a particle really well, you have a lot of uncertainty regarding what its momentum is. You get the same thing with these lasers. You get it's just a Fourier transform. Anytime you have Fourier transform, you have these uncertainty principles. Whenever one is more narrow or more precise, the other variable becomes more spread out. But he was saying that even in the experiments, they're nowhere near like a big problem is that they know this limit exists, but they haven't quite reached it yet. Um, so they haven't reached like the physical limitation. They're having experimental limitations at the moment, and a lot of people are working to get these narrower so that they can approach kind of the more physical, like this is what physics tells us our limitation is, opposed to like we can only do experiments this well at the moment. But anyway, that might be something slightly different than this. But for the sake of time, we should move on to our main topic now, which is on photography. And Patrick, I think you're leading this one, right?
Yeah. So I've been interested in photography for a long time. I know Feely has as well. We both worked at one point at the same time for our old university as photographers. But it's actually really complex how these sensors work, and there's a very rich history of photography. And I think delving into exactly how we capture photos is really interesting, and there's a lot of chemistry and physics related to it. More so chemistry for older film cameras, and lots of physics and electronics, and even some computer science for the newer sensors. So to start with, um, images in their essence record the state of something as it was. So they're able to take in light that has reflected off something, and capture that. Now, whether it's over the course of a split second or over the course of days, whatever they're recording, they're collecting light. And this was something that was kind of a dream for a very long time for people, because we have these photos that some of which are extremely like hyper realistic, but they're just portraits. They've been painted by very skilled artists who have been able to recreate scenes or subjects beautifully, but that's not recording exactly what happened. There's still some artist interpretation there, and the photons that you see that have reflected off, say, the image or the painting, weren't the same photons that were initially captured. And there's a really good Veritasium video that I think the intro is like that, where there was a video of the host as a kid and saying that the photons that hit the host and then went into the camera were then saved to a tape, which were then converted to digital bits, which were then uploaded to YouTube and then projected from a screen into their eyes. So there's this continuous path that the photons, or that the information more importantly, takes as it goes from the subject to the recording device and then to your eyes. Now, this kind of dream was realized in 1826 when the first photo was captured, which was able to convert this information carried by photons. In this case, it was originally photons produced by the sun that then bounced off a structure and then into this original camera, and then it was saved through a chemical reaction onto a plate of a very special photosensitive chemical.
Well, the concept of light as particle is fairly new concept, right? I'm sure at the time they still believed that light were just wave, like how Newton thought about it, right? Because like the fact that we talk about photons are like it's very modern way to look at it.
What was around the year or the years that this photography first came around. I know way back in the day, wave and particles weren't even quite like a concept. There was some corpuscle or whatever they're called. These little it's some weird version of like particles, but not quite. It was a theory.
Crepuscular.
Yeah, that was like a theory Newton had, and it was
Well,
slightly
the
different than the idea of a particle, but similar in essence.
well, the word atom, this has been around since ancient Greeks, right? Like
Hmm.
the word atom mean indivisible, right?
Yeah, yeah,
Atom. So they kind of guess that the idea of having small, smaller stuff that made up everything has been around for a while. But in the same, I don't know if when you say particle, you mean like elementary particles that we know it. That's just a different thing.
yeah. I guess what I was wondering is that when photography first became a thing, what was our current theory of light, and what I don't know if that matters or not because I
I think
tend to
it's like
step
very
away.
Newtonian. It's like probably super Newtonian way of
Yeah,
thinking about light,
that's what I'm thinking.
which is wave, right? Like Newton's a huge on light as wave. Dude just figure out it's made out of colors and all different colors. You can
I
mix
thought he
things
had
with like
I
red,
thought he
green,
had the
blue.
little he had the corpuscular theory, not the way like that's what he believed, but maybe I'm wrong.
This might be better to discuss later on, but
Okay, okay.
in the early 1800s, they were trying to capture light, and I think it was so in 1826. I don't know if they saw light as particles at that point, but they were starting to develop lenses, and so they definitely knew that it was wave-like and was able to be refracted in lenses and focused. And so this first image was done on photosensitive bitumen, or the type of kind of raw oil that comes from the ground. And it was focused just outside a window for a couple days and was able to record this structure. Now, fast forwarding a few years and photographs start pop up more and more and more. Mind you, this was 1826, so throughout the 1800s, film photography was developed kind of slowly, especially compared to how things develop today. But the time it takes to capture photo went from a couple days to minutes and then seconds and then even fractions of a second. And this occurred because the chemical composition of the photosensitive material improved. And so faster images could be taken, meaning that less exposure to light was needed to actually make those chemical reactions happen. And so by the turn of the 20th century, we were able to take quite quick photos. And there's actually a famous series of photos of a horse running. And this was done by setting up multiple different cameras that were all on an electronic timer. So one would fire, then the next would fire. And they're all of a horse running. And this was to kind of prove that at some point during a horse's run, all the feet will be in the air and nothing will be touching the ground. And so this was kind of seen as one, the advent of slow motion, because you could see the horse running in these still frames. And also kind of for sports cameras, because you're recording someone running. But it really took until digital cameras that we could have really advanced slow motion and these very cool cameras.
Yeah, the electronic cameras, I think back in the days is like very expensive. Even films are expensive, right? But you can control a lot more with electronics. And one of the problem with slow motion photography is the lack of light. If you see like really high speed camera, and you see they have a lot of light in the studio. You can look up anything on YouTube. People do slow motion. If you look at their rig, there's so many lights, like so much light that they need to fill up the room, and have this specific type of light. You can't use like normal fluorescent light because that flickers for like 60 hertz. And so if you take a video or something, it's gonna be like light dark, right? So it's gonna be very annoying. And that's I think we in science we have some kind of like strobe light like that too, to create like the illusion of the water floating when it's not floating. Have you seen that? That's really cool, right? Like, but a lot, well, not a lot, but some people are sensitive to this kind of strobing effect too, like this really fast flickering light that you don't even notice sometimes.
Yeah, the lights in my house actually, you can't see it, but sometimes if you look in like certain directions, you can like it feels like there's a strobe going, that it has a kind of a rate that's so fast you can barely see it, but sometimes at the right angles and the right like lighting, you can tell it's happening. It's very faint.
Yeah, if you remember, like, early 2000 or 90s, like horror movies, there's a lot of those when the light flicker on, but it doesn't come on right away, right? It doesn't happen with the LED these days. You flick a switch, it's on. But then there you have to flick a switch and you see this like ember of like orange and yellow and start to flicker, and it 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 flicker fast enough, it looks as if it's a continuous light.
I will just say that some LEDs do flicker though. Like especially if they're plugged into a wall, they're on an alternating current, and the cheaper ones don't have a full bridge rectifier, which is able to convert AC to DC. And so since LEDs are a diode, they can let current go one way, but not the other way. So you can actually see them flicker sometimes, especially if you spin, like, maybe don't do this inside, but if you swing like cheap Christmas lights that are LED around, you can actually see them flicker. They'll light up in one region, but not the other when you spin them.
Well, I think my lights are LED and they flicker a little bit, but it's so fast that you can barely notice it. Um, and the other thing too, I know about optics and light and things a decent amount, I'd say, but I don't know much about cameras and photography and kind of, well, even digital photography, right? Like you see videos of someone taking a video of well, I guess it's not a photo, but it's a video, but of a helicopter flying by, and it looks like its blades are just not moving because cameras have refresh rates or rates at which they take videos, and I don't know anything about how that works physically or optically, but if you have that rate the same as the helicopter's rate as their blade spinning, then it just looks like it's not moving because you're only taking an image at the exact same time that the blade does a full rotation, so it looks like it's not spinning.
Yeah, so you get things like the rolling shutter effect, but
Hmm.
um,
Let's talk about some cameras more. Maybe I want to hear about
Well,
them.
it happened with your eyes too. When you see a car that's moving fast, you look at the wheels, right? You don't see it exactly. Sometimes you see it moving backwards, like like it's really strange. Like this type of things that happen.
Oh yeah, that's a good point. And your brain probably fills in a lot of it too, right? Whatever your eyes see, your brain does a lot of like filler work.
Well, when old movies, they kind of figured out around like 24 frame per second, so when people start to not notice it, right? That's why like people like movies and stuff used to be like 24, 25, 30 frame per second, and now we realize like, oh, 60s frame per second give a lot more smoother. So people say frame per second, what does it mean? It's really 1 second we stack up 24 images and run it within 1 second. So is what it mean by frame per second, like 1 frame each. So yeah, so these movies these days like could be like usually it's 30. That's like film standard, and 60 has some. Some would say it's 29.97 is hilarious. Because I think did we talk about that before in this podcast? Because I think that's an artifact from the fact of the color television. Because back then the frame per second is 30, but you need to encode more to be able to insert color. So they have to basically cut in signal of color somewhere. That's why 29.97. But that's a little bit of fun fact.
I I I don't know about that very much, but I know in like gamers, people who play a lot of video games, they're very concerned with their frames per second. So like I think 60 is like good, considered good, but 120 is considered really good, and maybe there's even higher ones, but anyway.
yeah. So all these things, especially frames per second, derived from physical film that you had chemical reactions happening on and were able to record. And you were limited in some cases by the film and the amount of light, as Feely said earlier, that you could capture in that 1/24th of a second or a split second. So we wouldn't talk about too much film today. It's very cool how the chemical reactions work and how the light interacts with it and the different filters that you can apply. And that's how we got color film and color images. But we'll more so focus on the electronic side of it because that's what a lot of people are familiar with. almost every camera out there, especially on cell phones or your digital single lens reflex or your mirrorless cameras, those are all digital cameras. And to start for digital cameras, we have to go back in time to the early 1900s. And with many things in physics, especially modern physics, we get to talk about Albert Einstein, who I have accidentally written as Alberta Einstein.
Oh my god, you made the same mistake Hussein did, one of our old
Oh, God.
professors in our third year particle physics class. He wrote Alberta Einstein. I have a photo of it, of his slides that said it.
He also lived in Alberta.
He also supervised you, right?
He did.
Oh my god, you made the same mistakes as him. What a wild
Yes.
world we live in.
Anyway, going into Albert Einstein, the German physicist and mathematician, he actually won the Nobel Prize for something related to digital photography. However, this was far before it became a thing, and this was the photoelectric effect.
Yeah, it's funny how Einstein revolutionized, like, just changed physics completely and is everywhere. Like these Bose-Einstein condensates, like we talked about the other day, and general relativity, they're all kind of, he had a huge thing. But the photoelectric effect was his Nobel Prize, and it was kind of like one of these preliminary quantum mechanic things that, although I don't think he explicitly did any quantum mechanics calculations, he used an idea from quantum mechanics that um basically that like these particles come in little chunks, the particle nature of light instead of a wave. So that was a big problem, was that, I mean, sorry if this is what you were about to say, but photoelectric effect, when you treat light as a wave, the calculations don't match the output. They don't match the experiments. But then Einstein said, okay, what if I take this idea that particles are little packages of energy? They're discrete little chunks of light, and if you do that, you get a theory that matches the experiment. And I don't think that was his idea. Some other physicist had it somewhere, and he kind of copied it. I forget who, but that's what he got his Nobel Prize for.
And that was the 1921 Nobel Prize. But for the photoelectric effect, in essence, what it describes is that when you have a certain frequency of light hitting a metal or a semi-metal, which we'll get into a little bit later, it can eject electrons from that metal. So, for example, if you were to shine a blue light onto a piece of metal, then you would eject electrons. Now, if the photon or the light that's being shone on the metal isn't high enough energy, so if it's more kind of towards the red range, it wouldn't have enough energy to eject that electron. Whereas there's a threshold in which the electron can be moved or in this case, ejected from the material. And that energy, that threshold is related to the frequency or the energy of the light that's coming in. And so if you have more photons or a higher intensity of this light, then more electrons will be ejected. And if you have a higher frequency than your threshold frequency, then the electron will get some kinetic energy. So it will start to move, and you can get a current from this. So if you have a lot of bright, say blue or ultraviolet light shining on something, a metal that's able to undergo the photoelectric effect, then you will start to get a current. Now, this current could be small, it could be quite large. An example of a larger current would be photovoltaic cells or solar panels, which utilize the photoelectric effect to produce electricity. And in some countries, they produce a lot of electricity. Whereas if we look at something like cameras, they produce very, very small currents. And so with Einstein and his first ideas, this was with metals, but we found that using semiconductors, we can also get similar results where we can create this very small current that can be used to determine how much light actually hit the semiconductor.
Sorry, Einstein got his idea from Planck. I just wanted
yes.
to. Yeah, Planck solved that whole ultraviolet catastrophe thing, and that's why black body spectrums are called Planck spectrums. But anyway, he got that idea from Planck and led to all this, and here we have photography.
Yeah. Although, if you want to read more about that, the first paper in The Dreams That Stuff Is Made Of by Stephen Hawking, Planck's paper is the first, where he describes like essentially quantization of energy, and then the second paper in that book is the photoelectric effect.
My microphone that I'm speaking into right now, I prop it up with a bunch of books, and the dreams that stuff is made of is the book that my microphone is on right now. Incredible. Yeah, I can open it up,
You stand on the shoulders of giants.
and they're books.
But anyway, so these digital methods of recording light took a while to actually incorporate, but through the work of Willard Boyle and George E. Smith, who were working at Bell Labs at the time, they were able to utilize some of this information to produce what are known as charged coupled devices, or CCDs. Now, specifically, they were working on metal oxide structure capacitors. So these were kind of like a precursor to semiconductors, but they used metal oxides. So a very common metal oxide is iron oxide or rust. But they were using them to store energy or store a voltage in some way, which is what capacitors do. And so they found that an electric charge could be stored in the capacitor, which could be possibly used as some sort of digital memory or analog memory even. So what you could do is you could apply a very small charge and create a potential difference in the capacitor. And then depending on the value of that, you could use that to extract, okay, this certain amount of charge in the capacitor relates to this, whereas a different charge relates to something else. Now, the really neat thing about this is that these capacitors could be coupled all in a row or in a 2D matrix, in which they essentially can transfer their information in this kind of step-like function, where the information saved in one capacitor transfers to the next, and then they all kind of shift down one. And that was a really revolutionary thing with the charge-coupled device, is it could store this data, and then you can extract that information by essentially moving the charges down one by one. Now, to actually produce a CCD as we know, and able to record images, is by placing a photosensitive material on top of the capacitors, or these metal oxide capacitors, to be able to record a voltage based on the light that's hitting it.
Well, the sensors we've been using, at least after the 21st century came, are not CCDs anymore. I think they're all CMOS now, which is like complementary metal oxide semiconductor, which is a step, well, another, oh, I don't want to say revolution, but like another development that came out of, well, to take over the CCDs, even though back in the day, CCDs are more accurate. It doesn't, it just have a slightly different technology, but it has been dominating the CCDs market now. Like everything just CMOS now.
Yeah, we definitely have more on CMOS sensors, but CCDs were the first ones invented in the 1950s, and so they were used a lot until the CMOS sensor was able to be produced and actually functioning. And the first CMOS sensor was actually produced around the same time, but it took a lot longer to catch on because of the way that they work.
Well, also like the way they manufacture it, because you need like really like micro manufacturing. Be it from going from the lab to commercial is a big step.
We also talked about semiconductors a bunch last episode, right? So good planning on your part, Patrick. Go
episode
listen
46.
46? Oh, not the last one.
Yes.
Okay, I got confused, but close enough.
Yeah, I'm pretty sure it was 46. So go check that out if you need a quick refresher on semiconductors.
One of them.
But essentially, these CCDs had a semiconductor photoactive layer, and it was a doped semiconductor. So there was a slight bias in it. And so when light shines onto the semiconductor, there's some electron movement happening, which then produces a potential difference within the capacitor. And the intensity of the light is directly proportional to the charge that is saved within the capacitor. Now, for example, when you're taking an image with a CCD, you have light shining onto it, and then you have to get that information off of the chip. And so what happens is that everything in the CCD shifts down to be recorded. So it's able to go from one capacitor to the other, and the next, and the next, and the next on the line until it's all outputted onto something. And so, for example, if you are older than someone born after 2000, you might be very familiar with VCR and videotapes. And this was one of the ways in which we could store this data in an analog style. So instead of like modern days and converting it to digital, we could just take what was ever shown or whatever illuminated the CCD, and then just transfer that right to a tape. So we had a way to record this data in an analog method that then could be read, such as what you see in a VCR. But the original tapes were much larger and much less information dense.
One of the main difference to when you do CCDs, well, I don't think people really develop CCDs anymore. I think they're kind of almost like a dead technology. Unfortunately, right? But I think because the development of CMOS sensor has become much more efficient and cheaper, they're arguably could be better. I mean, for the high end stuff, they could be because you can control the size better. You can have better frame rate or like better sensitivity, and the process is much faster because in the CCD you transfer from photons, you try to create electrons from it. But the CMOS sensor adopt a slightly different strategy rather than, have all these photons come create electrons and then process at the end, at the output node. The CMOS, basically each pixel has the photon comes in and all the process in the pixel itself and send out the signal. So you can see why it can be more utility when it comes to CMOS sensor.
Yeah, so CMOS sensors, each have their own pixel, but it really depends on the transistors because each pixel has its own set of transistors that are able to amplify this initial signal that's produced. And so instead of using this mixture of capacitors and photosensitive semiconductor, they instead, for the most part, just use transistors. And so you're able to record an entire image at once. Now, they still do kind of work in a similar manner to CCDs where the way that it's done creates essentially row by row the data is recorded, but some very advanced sensors, especially in high-speed cameras, are able to essentially take a whole image at once and record it. But that's more so of a data transfer issue than the capabilities of the CMOS sensor.
Yeah, I think I don't know if I used CCDs before. Maybe I have at some point from like old cameras. But one benefit of CCDs is less prone to noise because, any light could come in and trigger things in CMOS, but CCD, the threshold of triggering, I think, is higher.
Yeah, and that's a very important thing, not only with commercial cameras, but also in scientific instruments, is your dark noise. So dark noise is when you have no light coming into the sensor at all, but you're still getting some sort of signal. And so these CMOS sensors are more susceptible to dark noise because there's a lot more electronics. And for example, if you have some sort of electromagnetic wave coming through that interferes with the electronics, you can get dark noise. Or if there's just each transistor is very slightly different, they aren't all created equal, there might be some noise from that. So for example, when we're trying to do hyperspectral recordings from of different objects and trying to get their spectra, dark noise is something that's very important to record because within some wavelengths of light, you might get more dark noise than other wavelengths. So it's important to calibrate based on that. Whereas CCDs don't have that issue as much.
Yeah, and I think CCD is more analog per se because it is analog converts into this analog signal. But for the CMOS, it hit the pixel. It has the analog to digital converter inside each pixel, so things become digital real quick compared to the CCDs where things remains a little bit of analog. So it's kind of help if you like that kind of tone and the feels. These days, not really about accuracy anymore. There's so much post processing in anything you do. Your phone does more post processing than any machine ever seen, right? Like phone camera. You ever work with a professional camera, you realize the raw image is so, it doesn't look anything like what we see when you take a phone and take a picture. Like it's so much processing that's going through it.
Yeah, and that's another thing is the scalability of these devices. So CMOS sensors, a lot of work and research has gone into them. So we are able to fit them on a phone, or I've even seen pills that people can swallow that have little cameras on them. So you can record your digestive system, and essentially instead of doing a colonoscopy, you can just swallow this pill and get very similar results. So the size of them and the fact that we shrunk down transistors, again, see episode 46 for this, allows us to essentially miniaturize the technology. But I do just want to mention, because it looks like we're running out of time soon, that Boyle and Smith actually ended up winning the Nobel Prize in 2009 for their invention of this imaging semiconductor circuit, which went on to become the CCD. Now, it's kind of wild to think that they made this discovery in the 50s and didn't win the Nobel Prize until 2009, so luckily they were still alive. And they actually shared this Nobel Prize with another person that year. His name was Charles Cow, and he actually won it for fiber optic transmission, which is what we talked about earlier in the episode. So two very different things, but important for data transmission and recording.
Well, I know we talked only about the sensor so far, but like photography also has a lot more physics in it, right? Like lens, for example, there's so much optics that go into it. How do you make sharp images? How you deal with aberrations? What's depth of field? What's the focus? How you design that even? Why is a lens is so expensive? Right? Those you can have like really short lens expensive. You have like telephoto lens can be very expensive. Well, why would that be expensive? And even furthermore, like how do you control the shutter? Or these days we have something called mirrorless with no like rotating mirrors we found in like what's called DSLR cameras, you know. Um, and also like how flashes work. The flash has evolved so much, and do we need them anymore? And there's so much physics that in photography that at the time I was really interested in it. But the more I learned about it, the less I was interested.
Yeah, I think we'll have to maybe say this is a precursor to a future photography episode, because there are a lot of physics that would be cool to discuss. Everything from capturing light to what the limits are of photography. And we have talked about telescopes in the past, but no, I think talking about photography more in general is a good idea. But yeah, overall, the CCD, very important. CMOS, even more important as we become more and more, I guess, involved with everyone and recording everything that we do and starting to use all these sensors for things like car safety. Like I know a lot of cars are now going to computer vision instead of radar and LiDAR for their driverless functions. So it will be very interesting to see if there's another thing that comes up that's not a CMOS, not a CCD, but something that's even better and can be used even more.
Yeah, it's pretty amazing how far photography's come. So I thought today's episode was going to be more on what Feely was saying, like more of like the physics of cameras and things like that. But I'm going to hold you to it, and we're going to do an episode on that at some point. Photography episode 2. We had an episode at one point where we talked a lot about the human eye, which is definitely related to cameras in some ways, how they function. But like even the camera on my phone, right? Like the quality of its photos is just so crazy compared to even like what was considered a very good camera years and years and years ago. Everything's so small now that you can fit it into your pocket. But yeah, thank you for that, Patrick, and also thank you, Feely. You guys both know a lot about photography, and I don't, so it was very good hearing about it. So before we get to our main story, which I think Feely has prepared, Patrick, how do people reach us?
Well, thank you for asking, Liam. There are many different methods in which you can reach us, the main of which is our Gmail account. So if you have any questions, comments, concerns, queries, or you would like to be a guest on this show, talking about whatever field you specialize in, we would love to have you, and you can contact us. We're hyperthesispodcast@gmail.com. We check it quite regularly, so send us an email and we will be sure to respond. You can also find us on Instagram. We're at the Hyperthesis, where we post content, including updates about when episodes will come out, or if episodes might be a little bit delayed, as it was for the episode 46, talking about semiconductors. You can also find some dank memes, as the kids say. So feel free to give us a follow, like, and you'll receive updates. We are also on YouTube. We have some excellent videos that are fun to watch and have all our recordings, so you can listen to them on YouTube. You don't need a podcasting service. If we're caught up or not, you can still find past episodes, and you can leave a comment, you can like, and you can subscribe to our channel, and that helps support us. Just to know that you're watching us and that you are interacting with the content, I think is what YouTubers want.
Yes, you can call me out for my inflationary cosmology mistakes.
All of them.
Yes, please do.
And of course, if you are listening to the podcast, which you are doing right now, congratulations, you found us. If you want to share us, we are on whatever podcasting service you may be able to find. We are on Google Podcast, Apple Podcast, Audible, which I think is now Amazon Music. Don't quite know that situation. And we're based out of Spotify. So you can find us wherever you listen to your podcasts. So feel free to share us with your friends. Ask us questions if you like, and if you are an expert in your area of research, we would love to have you on to talk about what you do.
All right. Thank you for that, Patrick. Now, our story today, skillfully constructed by our very own Feely, will be on the history of color photography, I believe.
Yes, actually, today we talk a lot more on like digital stuff, but I want to bring back into the history on the analog part of it, because I think it's one of the, well, it's very important. And I took this from the Science and Media Museum in the UK. So they have a website on that. You can look it up. So we all know the classic tale of Isaac Newton, hopefully. So this scientific investigation of what constitutes light and color began in the 17th century. So, well, I'm sure it began way before that, but this breakthrough came with Sir Isaac Newton then in 1666, where he split the sunlight with a prism to show it's actually a combination of bunch of colors, basically 7 colors of the spectrum. So, or what Liam knows way too much, rainbow. So it's been like that for a while. So nearly 200 years later, though, in 1861, a young Scottish physicist, James Clerk Maxwell, as we all know him, Maxwell equations, conducted an experiment to show that all colors can be made from mixture of red, green, and blue light. So that's pretty cool. So it provides some basics as how to deal with this type of light and whatnot. So not long after the demonstration, a French physicist, I'm going to butcher the name, Louis Ducour-Duhaurin, announced a method of creating color photographs. Like, okay, so by combining colored pigment instead of light. That's interesting, isn't it? So you can have black and white negatives, but taken through a red, green, and blue filters. Interesting, right? You still have black and white photos, but you have 3 of them, red, green, and blue. So you can have used to make 3 separate dyed image, and you combined those images to give you a colored photograph. So it's actually a method. This method formed the basis of today's color processing, really. But this method, we call it additive photography. So you add different images together to form a colored picture. However, the modern ones, we use what we call subtractive now, and I will talk a little bit about it and explain why. So this was very important work that came out. However, it's kind of like it's really hard to do because you want to make 3 photos, right? 2 different filters. So you have to take 3 photographs at the same time. So exposure times were long. And these kind of materials that are sensitive to the different range of color were not really widely available because people don't really know how to make them, didn't really know well about this kind of nature of light and how to capture them. However, so later on, an American photographer and inventor, Frederick Ive, devised a system based on 3 color separation negatives, also taken through the color filters. So, so these negatives, when placed in a special viewer called a chrome stop, mirrors kind of superimposed image on 3 transparent and second set of filters that restore the colors. They call these the chromograms. And these results were quite fantastic. They're very effective in creating color photography, but they're very expensive and quite complex. So, Ive systems, even though it works, is too complicated. And so instead of making these like 3 separate images or exposure through like red, green, and blue filters, well, how about just make one exposure that to a filter that combine all 3 primary colors? So, well, what does it mean by that? So the first process that used this is invented by Dr. John Jolly in Dublin in 1894. So Jolly discovered this. So he covered a glass plate with very fine red, green, and blue lines, less than 0.1 millimeter, to create this 3-colored filter screen. So for us physicists, probably looks similar to like a grading, but with 3 different colors. So when take the photograph, this screen is going to be placed in front of a camera. Placed in the camera in front of the plate. So basically equivalent to a sensor, but for analog. So after the exposure and some processing, the black and white positive image will be carefully placed in a register with another filter. So the result of this was a color transparency, which could be viewed by transmitted light. So basically, if you shine light upon it, you can recreate the photograph. And it was introduced commercially in 1895 and remains on the market for a while. However, the limited color sensitivity of the plates means the results were not that great. So the problem is also sensitivity. So I want to talk about the ones that are successful. The first usable and commercially successful, what I mean by successful process, is called the autochrome. So the autochrome, I know it's a few people old enough that have used autochrome before, was invented in the early 20th century by 2 French brothers, Auguste and Louis Lumiere. Yeah, you might have heard of the last name of Lumiere before, right? It's like a really big name in photography, I guess, or photographic technology. So they have been experimenting with color photography since the 1890s, but they published their first article in 1895, the same year that they were to achieve lasting fame for the invention of the cinematography. But in 1904, they gave this first announcement or presentation to the French Academy of Science. And by 1907, they began to produce the autochrome plates. Well, even though, the reception was really great, people love it, but how were they so successful and how do they work? So the autochrome plates used were like very simple to use. No special apparatus for photographer. They can just use the same cameras they had. However, the downside of it is just the exposure times are too long, which means like you have to wait until basically that plate soak up light, which you have to wait a long time. However, the plate is usable. It's about 30 times more than the conventional plates. So it's quite a bit more. Even in like really bright light, the exposure of at least 1 second would need it. So everybody, if you take a portrait, had to be still for 1 second when it's super bright, which in like cloudy or like darker weather, it can take more than 10 seconds, or even exposure can take longer to like 30 seconds, which in the standard modern camera, you want to use at least like 1/30th of a second, right? And so this is the exposure issues of the autochrome. So how do autochrome work? So instead of having these lines of red, green, and blue, actually the process of manufacturing is super complicated, because they actually use the millions of these tiny grains of red, green, and kind of bluish, blue-violet grains to combine to this plate. Basically, kind of spread them out, try to make it evenly, like randomly, but not, try to make them uniform. However, like to basically accurately reproducing the color of the subject. So in theory, the grains were mixed and distributed randomly to the surface. But when you actually do it, the probability meant some grouping of grains of the same color is inevitable. So even though you don't see these grains with your naked eye, you can still see clumps and stuff when you take photos. So this kind of autochrome unique feature that maybe there's some more green, there means some more blue here and there, and maybe the total thing is not like more green than usual, that produce this very unique tone that the autochrome comes in. So when you look at the very old photograph, it may be a little more green, maybe there's like the skin tone look different, the color of the sky be a little different. It's from the fact that if you use autochrome with specific randomly distributed grain distribution, it's gonna give you a unique tone. And as a testament of how popular it is, by 1913, the Lumiere factory in Lyon was producing more than 6,000 autochrome plates every day. And this success prompted the appearance of many other processes based on this concept of like this screen made up of microscopic color filters. So you can use grains and stuff, or geometric patterns like lines and square, but you can also see this legacy as thinking of things as microscopic, colors that capture all the colors, similar to like pixels. So basically, this is a story of how an analog photography or capturing of light became basically the foundation of the modern photography and the way the sensors work.
Thank you very much for that, Feely. Interesting stuff. Yeah, so that was our 48th episode. Thanks for tuning in. We'll see you guys next time.
Take care.
Bye, everyone.
Booga booga.